any data architecture, there's a certain amount of challenges when you're getting started, moving data in, and obviously what I think most people are focused on, which is optimizing performance and reducing. For the first piece, there can be some intricacies when you're moving data in, right? If you have to bring data from like a tabular source or a file-based source of data, BigQuery has some good options for that. But what if your data isn't sitting in Google Cloud Storage? What if it's in a different cloud? And then it adds more complexity. Maybe you're pulling data from some other system. Maybe you're pulling it from analytics tool, web analytics, or maybe it's some other, location that's in a completely different cloud, that's in a completely different database. So there's all these kind of intricacies about how you want to centralize and collect your data, and doing that efficiently with sort of the most efficient right process to get that data in. So there's one piece there. And then when your data sets start to grow over time, of course, there's the element of managing cost. A lot of the cost in BigQuery will come from actually running queries. So there's two pieces to that: structuring your data really well so it can be efficient, and then ensuring that the people using those data sets are writing efficient queries and using that data set efficiency that you set up. So if you do those two things well, you can usually get what's the third bucket says here. You can optimize for query performance and reduce cost. So those are kind of those three things: making sure you're ingesting well, optimizing your data, optimizing your queries. And if you do those things well, you should be off to a good start.
That makes a lot of sense, right? So that pretty much brings us to the next part. Like, what are the best practices that one can use on BigQuery to actually get the best ROI out of? So
Yeah. So I'll talk about a few different methods here that I recommend, and then we'll go into a demo. This is we'll be looking at how this actually gets implemented, both bringing data in from the Hevo system and bring that into BigQuery, and then actually running and structuring these queries efficiently with some data that we'll talk about a little bit later. But the first thing, like, if you don't do anything else, don't use select star in BigQuery. That's like just a really simple rule. If you do anything, make sure not to do that. The main reason is that BigQuery's data is stored in a columnar data system. So the more columns you add, the more data you have to scan to write your query. So if you only pull the necessary column names, it will just look at those columns, and you'll greatly reduce your data cost in terms of the queries. So if you do anything, make sure you just remember that. That's a big, pretty easy tip to remember for writing that. So in terms of data structuring, there's two data structures that you can implement within BigQuery that can greatly impact your performance. So the first is partitioning. If you're not familiar with partitioning, partitioning is basically a way to split your data up based off of some common attribute. Usually this shows up if you're using like temporal data as a time element. That could be the day, that could be the day, like the hour of the day, if that sort of metric is interesting to you. That could be the year, whatever that is. That's a common one. That's not to say that that's the only one you can use, but usually that's what it shows up as. Now, on the left here, you can see the statement to actually create a partition. It looks more or less like a create table statement, except it has that extra line to create the partition. And when you actually write the query, you want to make sure that you use the partition in the where clause, because that will gain you your most efficiency, because it will only look to those particular partitions of the data that it needs. So it will eliminate everything else that's outside of that in the where. The other thing that you can do is actually clustering your data. And clustering is sort of exactly what it sounds like. When you cluster your data off of a component in your data, I think it's in the next, you can effectively group the data in the table by that condition. So imagine you have a data set of user activity. Maybe that's some sort of station or on a website or whatever that might be. You're partitioning by date, but within that, you're also going to cluster by maybe an event type, maybe user ID. You can cluster by multiple features. You don't want to do too many, otherwise it really doesn't add much value. So you want to limit that as much as possible. So clustering by that specific thing. This will really start to show up when you get very, very, very large data sets, because when it will look first to the partitions and then just for the clusters of data that it needs, it can kind of find those a little bit more efficiently when it's doing the table scan. So the next one here, optimizing the where clause. So this is where, if you're in a data engineering type of position or working on ETL or anything like that, this is where you can make some pretty impactful gains just by changing data types. And I think it seems like a very small thing, But one here is actually within the where clause. So BigQuery works really well with where clauses that are optimized for specific data types. I believe there's three in total. There's or like a date or a timestamp. There's a Boolean and an integer. So if you can transfer or transform data types into those data types, maybe that's by encoding, maybe that's by some different method, that's going to get you a lot more value and a lot more performance. So this is a really, I mean, a trivial example. If you have, you're tagging your data as someone is true as yes, and you can change that to a Boolean, that's something you should do. But another example that we can actually look at or showcase within the data that we're looking at is it's New York City 311 data, and each row is basically tied to a specific borough of the five boroughs of New York City, being Brooklyn, Queens, Manhattan, the Bronx, and Staten Island. And you could actually encode those 1, 2, 3, 4, 5 and use those as integers rather than strings. So if you have some sort of quick recall there that you could write into your data structure, you're likely to get more performance there. So that's one kind of quick, easy tip. On the next slide, the order by is another important operation. Now, especially if you're creating some sort of report, imagine it's like a top 10 report, or imagine it's ordered by date, whatever that might be, you don't want the order by in the earlier parts of your query. You always want it at the end, because that requires some sort of data shuffling to take place. If you BigQuery, or I mean, really any system, if you have to reshuffle your data, that's going to be a more expensive operation. So you want to move that towards the end. So on our left side, we have an example of a query with a CTE at the top, where the order by is happening in the C. Usually you want to use a CTE to filter your data that's coming down lower in the query. So if you kind of think of a query as a funnel, use that CTE to filter your data. Definitely don't do a shuffle of your data up there. That's really not a good idea. What you can do here is you can see it in the correct structure is that we're actually going to filter it to a specific date or a range of dates, and then move our order by to the bottom of the query. So we're only doing that at the very end. So with the smallest amount of data, we do the order by, and that allows us to do that way more efficient. Another common thing is I see a lot of, if you're more of an analytics engineer, data scientist in that role, actually using end data. If you just want to look for like the existence of something in the data, usually using like a count star and then searching for it in a where clause is usually the way you think you should do it. What happens there is that it has to actually look over the entirety of the table to do that count operation, because you're telling it to count every single instance, right? But if you just care to know if something like that exists in the data, you can use this special function called exists, which is in BigQuery. And you effectively call it as a subquery. So you call select exists, and then you can select a data value such as name, and see where user ID equals 1, 2, 3, 4, 5. So my question here is, does user ID 1, 2, 3, 4, 5 exist in the data? And then it will scan the table. And once it hits that point, it will actually stop running. And that will complete the query. So you're scanning far. You may end up, if that number happens to be at the very end of your data set, they're comparable, but usually it's somewhere else in the data set, and you can process less data, which in turn process less cost. So another really nice one is approximate aggregations. Now, there's a whole set of like approximate aggregate functions within BigQuery, and they sort of take the place of costly aggregate calculations or things like that. So good. The one I chose to highlight here is the use case of counting a distinct value or attribute in the table. What you can see here is we're trying to count the number of distinct user IDs within that. And that basically requires to scan everything and count everything and do all of that. The approximate count distinct does it a little bit differently. If you go into the BigQuery documentations, you can actually understand how it does that, but it's far more efficient, and you can scale that a lot further, especially on very, very, very large data sets. So if that's a question you need to ask over a large chunk of data, make sure to use those approximate counts. They're going to be a lot more, they're a lot cheaper and a lot faster. So and this is pretty important when you're doing joins, because you're inevitably going to be joining data from multiple tables. There's in these examples, we have about users, or maybe data about purchases, or data about activity. Those join conditions, you want to make sure you're joining them based on the most efficient, once again, data type, right? So joining or using a where condition of a string. And just a general rule of thumb, strings and these bigger data types are going to be a little less efficient than the smaller data types like Boolean, date, integer, right? So if you can, you want to join them a little bit more efficiently based on those data types, which you can see highlighted in yellow here. The other thing that you can do is actually wrap those in CTEs. Like I said, thinking of your query as a giant funnel, these, in this left-hand example, we're not filtering anything out. We're joining the entirety of those tables together based on the where conditions and the join of, let's say, user ID. And we can imagine that, and on the left-hand side, user ID is if you can change user ID to an integer as a data engineer, you've just saved your company a lot of time or sorry, your users a lot of time, your company a lot of money. So that's one thing that on top of that, if you're someone writing the query, making sure you're using CTs effectively. For our filtered users, we're putting that user condition in the CT at the top, and we're also putting that in the second CT and then joining those smaller CTs in the final join. So you're optimizing both the join conditions at the top with the smaller data sets and then the join condition at the bottom with the integer based. So that's a very common one that I see a lot of mistakes with. In the next slide, this works very similar to partitions it's called a table suffix. If you know explicitly that your table is going to be written, or a subset of a table is going to be written in on a regular basis, maybe that's every day or something like that, you can actually use this table suffix when you're writing that in. And BigQuery will basically automatically recognize if you write a table. So imagine on the left-hand side, we just have this giant purchases table, and we have to scan that entirety of that table based off of that date, right? So inevitably a pretty inefficient operation because we're still scanning a lot of data. By using the table suffix, you're actually basically putting in a date stamp at the end. So you can see here's 2023 1001. So October 1st, 2023 is the last part of that table, purchases table underscore, and you're putting that date string at the end. BigQuery will pick that up and recognize that as a date, a valid date. And you can actually use this operand at the end, say table suffix between those two dates. And it works just like the where clause, but it's a lot more efficient because you're just filtering into those specific tables. So it's similar to a partition, but if you're doing something on a very consistent basis, that works a lot better. I did this with a data set I was collecting every day of snow depths in the US. And it worked great. Like it was just super, super fast. And the query times the query sizes were a lot smaller. And then the last one, we'll actually show this one within the context of the data. If some data inevitably has string data associated with it, or specifically like long form text, right? This could be even something like a struct or, parallel to like a dictionary or JSON, or even if you have that long text field and you need to find something in that field, this is what the query you'd probably write on the left is like username, and using your wildcards to find the name John, right? There's actually a function called search that can search across any string data type or even like a dictionary or structure, I should say, or an array, and you can use that specific search term. We'll look at that because the 311 data has these like outcomes in them, and it's text data that's entered by the different places. So we can actually search that, and it's a full text search. So it's a little bit more of an algorithm. You're going to get better results. You'll catch edge cases, and it's more efficient. So if you ever have to use, text data, that's the one to go with.
In the next section of this webinar, we'll be just going through the ELT, how as a user, you can also reduce your ELT costs, because that's one major part of moving that data in from your various source systems to your warehouse, where you can actually get some gains, utilize different tools, and have some best practices to actually control costs while assuring you're able to meet your businesses and your customers' needs. So we'll be going over a few of them right now. The first one is optimizing your data ingestion frequency itself. So while you are writing the data to your warehouse, deciding how often you run your workflows, how often do you run your ELT workflows, are directly going to impact how often your downstream systems eventually end up processing this data. And if your idea is that you need data not that often, maybe you should not run it. That itself can pretty much add to significant gains. But it's not just about how often you load it, it is what data are you loading. So there are a lot of scenarios when you might be dealing with data which might be incremental, might be a full load, might be something which has CDC capabilities, and there will be scenarios where it does not. So that's where tools like Hevo come in. We are able to easily get in data incremental data from a various set of sources. Let's say there are different scenarios when you're dealing with tables, which and where you do not want to read from logs, but you can actually write custom queries, or you can have a table mode query which can have a special offset to actually get incremental only data. Then the next part is leveraging cloud storage and compute. While BigQuery offers this out of the box pretty much, where storage and compute are segregated, there are other possibilities as well, where you can use S3 as a destination with Hevo, where you can write data in S3 and then use different compute engines to actually run past it. But I mean, for BigQuery, you pretty much get it out of the box, and that's why it's so special. Then coming to batch versus real time. Now, Hevo is a native batch hybrid streaming engine where it can actually help you move data in a batch-based manner, loading it to different warehouses, whereas using stream processing, because we have Kafka underneath, to actually move data in streaming it directly from your source, and also writing to a streaming destination like Postgres, or to a batch-based destination like BigQuery as well as Snowflake. Now, these scenarios come in because writing something in near real time or as a stream can be a lot more expensive, whereas while dealing with something which is batch. So segregating your workloads correctly on what needs to be a batch, what needs to be a stream, depending on how often it changes, how much schema changes that it can face, taking that into account and then really answering that question can help you. In terms of cloud infrastructure optimization, so you can actually rely on a few more auto-scaling serverless architecture on your for your databases, where you end up paying only for what you use rather than a consistent RDS. So moving to something like Aurora, if you're depending on your scale, or truly serverless on either side, can certainly help you optimize both on both ends, on your source side as well as how your destination. Then managing data spikes. So this is something that Hevo offers out of the box, where you can actually set up data spike alerts. So let's say there are scenarios where you can pretty much set meters and quotas on what a particular pipeline can consume, so that suddenly one large spike or one big update on your source system does not actually take your cloud costs on your warehouse side, or your or on your ETL vendor side, like out of the roof, right? So having these controls over, just in case if there is a sudden spike which was not planned for, or which was pretty much an accident or a bug, leading to a big bill on your head. Then scheduling during off-peak hours. This goes hand in hand with improving your like relying on serverless architecture, while at the same time not taking too much load on your source systems, and ensuring that your ETLs are or ELT processes are running. The last one being utilization of alerting and monitoring. So generally, when you're dealing with any ELT, your post-load operations are fairly expensive. So ensuring you only to prevent expensive reprocessing of your data by getting alerts of any issues. So setting up that monitoring certainly helps, so that you do not like run up your bill on your data processing.